one more example of finding the curvature. Let's see, we'll just go ahead and use that formula for the curvature, which is to find the derivative of the unit tangent with respect to t and take its length, and then divide by the speed. So in order to do that, first we're going to need to find the unit tangent. So the unit tangent is going to be the velocity divided by the speed. So the velocity is this derivative. Let's see, we have 3 root 2 over 2 times sine. So that's going to be 3 root 2 over 2 times cosine t when we take the derivative. And this next component is the same, so it will also be 3 root 2 over 2 times cosine t. And this derivative will be minus 3 sine t. That's the velocity. Now we need to divide by the speed. So let's see, we get, this is essentially 1 over root 2, so when you square it you get 1 half, and that's 9. So we get 9 halves cosine squared t plus 9 halves cosine squared t plus 9 sine squared t. But the 9 halves cosine squared plus another 9 halves cosine squared makes a total of 9 cosine squared. 9 cosine squared plus 9 sine squared is 9. And so the speed in this case is 3. So that means that our unit tangent is, if we divide everything by 3, it's root 2 over 2 cosine t, root 2 over 2 cosine t, and minus sine t. Then dt dt, the unit tangent d time, is going to be minus root 2 over 2 sine t, and again minus root 2 over 2 sine t, and the derivative of minus sine is minus cosine. So the length of dt dt, which we need for kappa, the length of dt dt is going to be the square root of, if you square root 2 over 2 you get a half, so we get 1 half sine squared t plus another 1 half sine squared t plus cosine squared t. 1 half sine squared plus 1 half sine squared is 1 sine squared. 1 sine squared plus 1 cosine squared is 1, so we get the square root of 1, which is 1. Okay, so now we can assemble this. Kappa is going to be this length, dt, the length of the unit tangent d time, which we found was 1, divided by the speed, which we've already calculated that the speed is 3, because we found the velocity, and then we divided by the length of the velocity, which is the speed. So now we know that kappa in this case is 1/3. We have a constant radius of curvature. In this case, that's because this is actually the parametrization of a circle. If you look at this, this resembles very much the equations for the spherical coordinate system, right? X is equal to rho sine t cos theta, and y is equal to rho sine t sine theta, and z is equal to rho cos t. Here I've just replaced phi with t so you can see the resemblance. Now if you replace the rho's with 3's, so you fix rho, you're going to be on the sphere. If you fix theta at pi force, then in both of these cases you'll get root 2 over 2 and root 2 over 2. So basically we've fixed rho at 3, so we're on a sphere of radius 3. And on the sphere of radius 3 we fixed theta at pi force. So we fix theta, then we just get a circle like this. Okay, and since it's on a sphere of radius 3, the radius is 3, so that's the radius of curvature, and kappa is 1 over the radius of curvature, and so kappa is 1/3. Nice little confirmation of our answer there. We found kappa.